The very beginning of this unit, we identified 4 properties of waves that were exhibited by electromagnetic radiation. We had refraction, which was the bending of EMR. We had polarization, which was the filtering out of components of EMR. And then we had diffraction and interference. I want to talk about those last 2 in a little bit more detail today. Diffraction, you remember, is not the bending of a wave due to the change in speed when it goes from one medium to the other. That would be refraction. Diffraction, if you remember from Physics 20, is the spreading out of a wave around a barrier or through an opening. So we've got a wave here, or waves, I should say, that are coming from the open ocean here to this barrier. But there's an opening in that barrier. So there's a little bit of the wave that goes through the opening. It's going to look something like this. But the wave just doesn't go through here with calm water over here. The wave, as it goes through the opening, spreads out. So we've got an actual photo of real diffraction taking place, the spreading out of a wave here as a result of it going through this opening. Remember, the wavelength doesn't change, the angle doesn't change, the speed doesn't change. We're just spreading out, not changing direction or changing speed. That's diffraction. Now, if I have diffraction taking place as a result of 2 openings, let's say I was to have another little opening right here, then what we would end up with is a phenomenon called interference. When I have 2 sources and 2 diffractions that take place, then I get areas of constructive and destructive interference. So let's say we've got an opening right here and another opening right here that you can't see. We're going to produce diffraction as a result of this one. We're going to produce diffraction as a result of this one. And as a result of both of those crest and trough patterns interfering with each other, we're going to get areas of constructive and destructive interference. Constructive interference when crest meets crest, or trough meets trough. We're going to get destructive interference when crest meets trough. If you look at this diagram, you can see pretty clearly areas where we have constructive and destructive interference. Right here is an area of constructive interference. This is where we get bigger crests and bigger troughs as a result of the crest and the crest of one diffracted wave interfering with the crest of another diffracted wave, or the trough interfering with a trough. Constructive interference. Same deal here, constructive, same deal here, constructive, and so on. Where we see these big ripples, we have big crests and big troughs corresponding to constructive interference. But then in between those, we have these areas of destructive interference where the water appears to be pretty calm. So we have alternating areas of constructive and destructive interference. Now, if we're looking at this as a water wave, like the photo up on the board here, then you can clearly see those areas of constructive and destructive interference. But if we're looking at light waves that are doing the same thing, and light waves do the same thing, we established that on day 1 of this unit, then we're not going to actually see these patterns of alternating constructive and destructive interference. Light must reflect off of something in order to see it. So with water, we see the pattern that you see up on the board right now. With light, you don't. In order to see it with light, you have to put a screen somewhere. Let's put a screen up here. Just a white paper or board or anything that can act, anything that can cause light to reflect off of it. When we do that, what we end up with on that screen is a bright spot where you have constructive interference. Another bright spot where we have constructive interference. Another bright spot where we have constructive interference, and so on. Right, where you have crest meeting crest, there's lines of constructive interference. We don't see them until they reflect off of something like the screen. When they do, we see a bright spot. Bright light corresponding to constructive interference. But in between all of those areas of constructive interference, we get a spot, I call it a dark spot, but it's really just the absence of a bright spot. Where there's destructive interference, there is no wave or there is no light. So we get a bright spot, a dark spot, a bright spot, a dark spot, and so on. Alternating areas of bright spots and dark spots. Does that make some sense? By the way, we call them bright spots here right now, but we could also call a bright spot an area of constructive interference. We could also call it an antinode. We could also call it a maximum, as opposed to the dark spots or the areas of destructive interference in between the bright spots that we might call, besides the dark spot, areas of destructive interference. We could call them nodes. We could call them each minimums or minima. So with water waves or any kind of other visible wave that doesn't need to reflect off of something to see it, we don't need that screen because we can just stand above it like we are in this picture and view the areas, clearly the areas of constructive and destructive interference. But if we're dealing with light or any kind of EMR that can't be observed unless it reflects off of something, then we need to put the screen in there to cause the light to reflect off of it. And when we do, we get these alternating areas of bright spot, dark spot, constructive, destructive, antinode, node, maximum, minimum, and so on, and so on, and so on. The diagram you see on the board now is a more formal explanation of what we just gave you, okay? As opposed to showing you the picture of the water wave, we're showing what actually happens with light. So the light is coming here from this direction. It's going through two openings, and of course it diffracts around this opening. It diffracts around this opening, and you see the diffraction patterns of both of those. But then you can see as they overlap that we get interference. Where you see these black lines here, we have constructive interference. And then on the screen down here, we have a bright spot that corresponds to that area of constructive interference. Same deal right here, same deal right here. But in between those areas, we have these areas of destructive interference, these white lines. I'm going to trace over in green here, where we see a dark spot, and then a dark spot over here, and then another dark spot over here, and so on and so on and so on. If you were to look at the pattern with what we call monochromatic light, one color of light, in this case red light, then we would see alternating areas of bright red, dark, bright red, dark. Now, if we had what we call polychromatic light, which is more than one color of light, the pattern's going to look a little bit different, but we'll talk about that tomorrow after we've had a chance to go over some equations. One more page that I want to show you here, and then we'll wrap it up for the day here. If we were to plot a graph of intensity versus position, so not literally just looking at the screen like you are right here, but you're to plot a graph of intensity versus the position, intensity on the y-axis, position on the x-axis, then it would look something like this. Now, I did this in Microsoft Word where it's kind of hard to draw pictures. It should be rounded kind of at the top. Okay, proportions aren't perfect, but you can see that we have what we call a central maximum in the middle, which is a bright spot, a high intensity spot of light. And then right next to that, we have what we call a first order minimum. That's a dark spot. And then right next to that, we have a first order maximum. And then we have next to that a second order minimum, where it's a dark spot. And then a second order maximum, which is a bright spot. And then on the other side, we have the same deal, right? We have a first order minimum, first order maximum. We have a first, second order minimum, and a second order maximum, and so on and so on and so on. Now, it doesn't go infinite to an infinite number of max and mins. You could figure out how many max and mins that we'd have, but that's a topic for another day once we learn some equations. The bottom line is it would keep going beyond the first and second order max and min, usually at least, depending upon certain circumstances.